the last class, we have seen how to decompose a non-singular matrix A into a product of a lower triangular matrix and an upper triangular matrix. That is, A can be written as LU. That's what we call it as LU decomposition. In today's class, we'll see what is a QR decomposition. Given a matrix A, we can decompose that matrix as a product of an orthogonal matrix and an upper triangular matrix. Orthogonal matrix we denote by Q and an upper triangular matrix we denote by R. That is, A can be written as a product of an upper triangular matrix and a lower triangular matrix. Let's recall what is an orthogonal matrix. A square matrix A is said to be orthogonal if A transpose equal to I or A transpose equal to A inverse. Then we have seen in many classes, last classes, how to construct an orthogonal matrix. Its column vector should be mutually orthogonal plus the magnitude should be 1. That is, if x1, x2, x3 are the column vectors of a matrix A, then x1 should be orthogonal to x2 and x2 should be orthogonal to x3 and x1 should be orthogonal to x3. That is, dot product of x1, x2 and x2, x3 and x1, x3 should be 0. That is, x1 transpose x2 should be 0, x2 transpose x3 should be 0, x1 transpose x3 should be 0. Further, we divide each vector by their magnitude. Right? We normalize each vector. Then they become unit vectors. Then a matrix composed with these orthonormalized vectors, we call it an orthogonal vector, orthogonal matrix rather. Right. This is what a QR decomposition is. Every matrix can be decomposed as a product of an orthogonal matrix Q and an upper triangular matrix R. Right. That is, A can be written as a product of Q and R. Further, if A is invertible, then that decomposition is unique. Else, decomposition need not be unique. So, the QR decomposition of a matrix is the decomposition of a matrix into an orthogonal matrix and an upper triangular matrix. If a QR decomposition of a square matrix, A can be written as a QR. Further, if A is a square matrix and non-singular, then the factorization is unique. Now, what's the issue? The issue is how to decompose, how to find a Q and how to find a R. Q, as I mentioned earlier, has to be constructed as an orthogonal matrix or should be an upper triangular matrix. Once you have an orthogonal matrix, getting R is a simple job. You can do it. There are many methods, right? One particular method we choose is Gram-Schmidt orthogonalization process. Suppose if the column vectors are linearly independent, we orthogonalize them. That is, we got a bunch of linearly independent vectors and we know how to convert them into a bunch of orthogonal vectors. And we have seen the process and we have dedicated one class for a Gram-Schmidt orthogonalization process, right? So we use Gram-Schmidt orthogonalization process here, right? So go back. Once again, learn properly how to orthogonalize through a Gram-Schmidt process. Then job is pretty simple, right? So suppose A consists of n column vectors, A1, A2, An, right? So my vectors are here, A1, A2, and An. Now, they are linearly independent, say. Now, with the help of those, by using Gram-Schmidt orthogonalization process, I need to convert them, with the help of these n vectors, A1, A2, An, I need to get new vectors, U1, U2, Un, so that U1, U2, Un are orthogonal. Here, they need not be orthogonal. A1, A2, An need not be orthogonal. They are linearly independent. Now, how to choose U1? U1, we take A1 as U1. Then, what is this E1? Normalizing. Once you have a U1, U1 by norm U1 is what we normalize, right? So that's what I call a E1. Right? Now, how to get a U2? E2 has to be, E2 is U2 by norm U2. Then what is U2? U2 should be orthogonal to U1, right? So U2, you need to project it on the space. U2 equal to A2 minus A2 dot E1 times E1. Similarly, U3 equal to A3 minus A3 dot E2 times E2 minus A3 dot E1 times E1 and so on, so forth. Here is a generic tool. UK plus 1 is AK plus 1 minus AK plus 1 dot E1 times E1 minus AK plus 1 dot E2 times E2 and so on, so forth, minus AK plus 1 dot EK dot uh, times Ek. That is, we are going to project it onto the space spanned by already orthonormalized or orthogonalized vectors, right? That's a Gram-Schmidt process. Let's then once you are orthogonalized, then we are going to construct the Q with the help of these orthonormalized vectors, right? E1, E2, En taking as columns. And once you have E1, E2, En, then getting R is pretty simple job. That is just a dot product. No? First column is A1 dot E1, A2 dot E1, and so on, An E1. And this is an upper triangular matrix. So all the elements below the principal diagonal should be 0. And this is how we get, right? Right. Once we have a E1, E2, En, then it's not hard to find. So the core process in here is a Gram-Schmidt orthogonalization process. Let's take an example. A equal to 1, 1, 0. That's a first column. 1, 0, 1 second column. 0, 1, 1 third column. Right. There can be 4 columns, 5 columns, and n columns. Right. For a hand computation, this 3 by 3. Tomorrow it can be 4 by 3. We'll see. We'll take an example in the next class with 4 vectors for them. Now, what's my A1? A1 is 1, 1, 0. A2 is 1, 0, 1. And A3 is 0, 1, 1. Now, I need to get a U1. U1 is nothing but A1. So, U1 equal to 1, 1, 0. I'm writing it as a row here. Basically, it should be written as a column because it takes a lot of space here. I'm just writing it as a column. For us, a vector is a column vector. So you have a U1, then E1 is U1 by norm U1. What is norm U1? Root 2. So 1, 1, 0 by root 2. So it is every component is divided by root 2. So this is my normalized vector E1, which I got from U1. Now, what is U2? U2 is A2 minus A2 dot E1 times E1. Right? A2 is 1, 0, 1 minus 1 by root 2 times this, right? And this is a simple arithmetic you can do very easily, right? Component wise subtraction that eats this E2. Once you have a E2, then find its magnitude, U2 magnitude. Then E2 is U2 by norm U2. So that is norm U2 is 1 by root of 3 by 2, this, and this is my E2. Now, with the help of U1, U2, or even E2, we'll get U3. U3 is A3 minus A3 dot E1 times E1 minus A3 dot E2 times E2. A3 is 0, 1, 1 minus, this is the dot product, minus A3 dot E2 is, this is the dot product, and component wise subtraction, this yields that. Now you find its magnitude. E3 is U3 by mod U3, and this is E. Now we got E1, E2, E3. Now let's our job is done. Let's construct our orthogonal matrix. Q is equal to, taking these E1, E2, E3 as columns. This is how we get. This is my Q. This is my orthogonal matrix. Once you have an orthogonal matrix, getting R is a pretty simple job. R is A1 dot E1, A2 dot E2, A2 dot E1. First row is with E1, second row is with E2, third row is with E3 dot product. But you know, all the elements below the principal diagonal should be 0. It should be something like this: 1, 1, 2, 1, and 3, 1, 2, 2, 3, 2, and 3, 3. Right? The dot product, this is my R. Right? This is one way of getting a R, upper triangular matrix. Or else, you can also get R like this. If A has QR decomposition, then A can be written as A equal to Q into R. Now we know Q is an orthogonal matrix, just now we constructed. So Q transpose equal to Q inverse. So what I do is I pre-multiply this both sides by Q transpose, then Q transpose into A equal to Q transpose into Q, which is I, then R. So my R equal to Q transpose into A, right? So you have a Q, then getting a Q transpose, just writing its rows as columns, columns as rows. Then this is my Q transpose, and this is my given A, and it is a matrix, simple matrix multiplication. It's a row by column. So 1 by root 2 into 1 plus 1 by root 2 into 1. So this is what I get, 2 1 by root 2's. And this row by this column, this, and this row by this column. Similarly, you do the multiplication. It's a simple issue. Then this is the R you get. So R you can get either by this way, or R you can get as Q transpose into A once you have a Q in your hand. So this is how we decompose a given matrix into a product of an orthogonal matrix Q and an upper triangular matrix R. Right? In the next class, we'll see a lot of examples, where A need not be a square matrix, right? We take a general matrix and we'll see how to decompose that as a Q into R, right? So this is how we do a QR decomposition.